Hello, Science 30s. I just wanted to throw together a quick example of a few energy mass equivalency forms of questions. So I've taken them right from our workbook, and this is the first one we have as an example of E is equal to mc squared. However, what we notice right from the data booklet is it is a little bit different. More specifically, it is this delta E is equal to delta mc squared, or this change in energy is equal to the change of mass times by the speed of light, or the speed of waves. If we remember, this c is a constant. It's 3.00 times 10 to the 8. And this is the fastest anything can go in the universe. So this is the speed that waves or light travels. So we're always given this. This is at the bottom of page 8 in our data booklets. For us, we kind of jumped ahead and we started with kind of the harder questions where we had to figure out the mass in a nuclear reaction. Here, we're already given the mass change, so we can skip the step of how we have to figure out mass. Instead, we're just using the change in mass, and we see that right up there. And so we can take that mass change and put it right into our formula. Now that we see it in our formula, we can just calculate it out. There's only one little twist, and that's the underlined part, where it says less than the reactants. And so in math, it's very important, and when we're using it, we put in that negative symbol. And that's what I wanted to highlight, is you want to put in a negative because you didn't destroy the mass, you didn't lose it. It's just saying the reactants was higher, products mass was lower. And when you go products minus the reactants, you're going to get a negative number. And it's not getting destroyed, because how do you have negative mass? So it's not getting destroyed, but for us, rather, it's getting converted into energy. And that negative part will tell us right here, and it'll carry all the way through, and that's where we get a negative number, because now it'll carry through when we calculate it. This negative number is a negative release of energy, and so that's the release of energy. We see that pop up where we have negative energy, and if we remember from Hess's law, anytime that we have negative energy or a negative number, this means it is an exothermic reaction, and that tells us this. And we could also just think, it's like, well, why do we do nuclear reactions? Well, that's because we want to release that energy, capture it as heat, and use it to create energy for us. I have another question for us that we have right here. So this is part of our practice, and I wrote in some of the other things that we need from our data booklet. So most times, every selected nucleotide, when we're doing a nuclear reaction, we will need our table of information, our masses of selected nucleotides, from page 8, where we're given all of them. Here, we were given extras that we don't always have from our table. And so I just chose this one. There is a B part, which you can answer on your own once you kind of follow the steps. Here, we have to first figure out the change in mass from the product side. So what we see over here, so we need to figure out the total mass on the product side. And then we need to figure out the total mass on the reactant side. Sorry, I flipped that. Sorry, we need to find red for reactants. That's why I grabbed red. And then we need to find the products here, of course. And we're going to see what the mass loss is. And so what we're going to use the uranium. We're going to use the neutron, which I wrote in here, which I got from our data booklet. And then we total them all up for the reactants, total them all up for the products, and we're going to see the difference. So as I scroll down, I wrote it all out for the reactants and products side. You can see here. Here is my reactants. Here is my products, a little bit more. This out of the way. And you can see how I added them all up. The one big thing to denote what I see here, I have a couple points to talk about. When you see the mass of the selected nucleotides, it is technically times 10 to the negative 3 kilograms per mole. And so when we go 1 mole times by 10 to the negative 3 kilograms per mole, our moles will cancel and we're left with times 10 to the negative 3 kilograms. We see that over here where we had 2 moles of these neutrons. So I need to go 2 times this 1. And we get our answer right here of 2.02. And that's what we're going to use. So we're not going to use this one. That's just to say we had to have 2 of them times by our neutron weight. All the rest are just 1. So this is the one case where we need to make sure we're timesing it through. And then we just simply add them up. On our reactance side, we have it here. We have our total mass of reactants in times 10 to the negative 3 kilograms. And then over here, we have our total mass of our products, which we should be able to get, which we have here. As a reminder, please pause as we're calculating this out. It does help to calculate it out yourselves. And so here, now we can see the mass difference is products minus reactants. And this is where I take my products that I had in purple. I take it here, subtract it from my reactants, which I have it here, and I get a difference of negative 0.20154 times 10 to the negative 3 kilograms. This is my change in mass. Remember, I didn't destroy it. I didn't get rid of it. I can't break that law. But what this is the change in mass, or the mass that changes to energy. Now, we did all this work to kind of get where we left off on that last question, to figure out this mass difference. Now, what we need to do is put it into this E is equal to mc squared. So I take my mass difference, I times it by my constant, and what I get is my change in energy. And I should get a negative 1.81386 times 10 to the 13 joules. And so this is a massive release of energy, which we capture in our nuclear reactor towers. Hopefully this helps. Hopefully you can go back, pause it, kind of walk through the 2 steps that I did. So I had the first step, figuring out the mass differences, which probably is the most amount of work. And then our second step, putting it is in, when we have a mass change, into our energy mass equivalency formula. Have a great day. Make sure to practice lots. Thank you.